Today, pressure of a gas part 2. Yeah, pressure of a gas part 2. Okay, the first part was about regarding kinetic theory of gases, and now we're going to prove the pressure of a gas based on the assumption of the kinetic theory of gases. Okay, let's look at this. An expression for the pressure exerted by an ideal gas can be derived using the kinetic theory of gases. Ideal gas, which is a gas that obeys gas law, and using the kinetic theory of gases, we're going to prove the pressure of a gas. Now, point number 3. Suppose an ideal gas, ideal gas in a cube of site L containing n molecule. Containing n molecule means based on the first assumption, which is a gas consists of large number of molecule. Okay, all right, so here is n molecule. Each of mass is m as shown in figure 9.1. A typical molecule moves with a velocity c, which can be resolved into component u, v and w. Okay, now in 3 directions. So component u, v and w in 3 direction is actually related to the assumption is the gas molecule are in constant free random motion. They are moving in free random Brownian motion, which we assume is x, y and z. Okay, respectively as shown. Alright, so I'm going to move it here. I'm going to explain to you here. Hold on, yeah. Just going to zoom. Okay. Alright, let's look at the first one. I've already pre-draw for you so that I won't take longer time to recording, yeah, because my laptop, my visualizer can only record for 15 minutes. Okay. Now let's look at this. We have a cube which is each side is L, 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 and moving we have 3 direction, which is x, y and z. Okay, so now we're going to solve and prove the pressure of a gas by looking for one molecule in one direction. One molecule in one direction, which is the x direction. Okay, so we have one molecule in one direction. We have one molecule and the mass is m. The mass is m. Okay, this molecule is moving with a speed of u or a velocity of u. Once when it hits the container, the wall of the container, it bounces back. It bounces back in the same u but in the opposite direction, which is the negative, and it comes back to this part of the container. So once it goes and it hits on the wall of the container, it bounces back. That means it's trying to tell us that this is an elastic collision, which is according to the kinetic theory of gases, which is number 3. The gas molecule collide elastically with each other and with the wall of the container. So it is based on the assumption of number 3. Okay, so let's find the change of momentum. Change of momentum is mv minus mu, correct? So mv is negative u minus mu, you will get negative 2mu. Negative means its direction, because momentum is a vector. This is the magnitude, this is the direction. Okay, so we have here is 2mu. We are only interested with the magnitude. Okay, time taken for a round trip. Time taken for a round trip, we know as v equals to s over t, the definition of velocity. Okay, so time taken for a round trip from this wall to the other wall. Alright, so t is equals to s over v. Alright, so s is 2l. Okay, from here to here is L, and then you come back, you bounce back, is another L, so it's 2L. B is the velocity, so it will be 2L over U. Okay, so time taken for round trip according to the theory kinetic of gases, it is in number 6. The time of collision is negligible compared to the time between collision. So what is number 6 is trying to say is, we are not interested with the time of collision, time during the collision happened. We are interested with the time between the collision. That means from here it goes here and it comes back here. So we want the total time taken for a round trip. Okay, now rate change of momentum. Now why did I put rate change of momentum? Because rate change of momentum is actually referring to impulsive force. Now why is it only impulsive force, not other force? Because according to the assumption of theory kinetic of gases, number 5, force between gas molecule are negligible. That means we are intermolecule forces are negligible except during collision. So except during collision, so that means only impulsive force is taken into note to prove the pressure of a gas. Okay, so here we have impulsive force is change of momentum over time taken. So you will have 2mu over 2L over U. Then you will get mu square over L. Okay, so we already finished the first stage. Now we're going to look at for n molecule in one direction. For n molecule in one direction, which is X. Okay, right. So first thing, let's look at this diagram. This now the diagram for one molecule in one direction. Now we have n molecule. Each molecule I put here 3 or 4. This is M1, this is M2, this is M3. So I'm going to make this Mn. Okay, so U1, U2, U3, Un. Alright. Okay, so U1 will have impulsive force F equals to M1 U1 square over L. So U2 will have F equals to M2 U2 square over L. So Un will be F equals to M and Un square over L. Okay, so total impulsive force will be M1 U1 square over L plus with M2 U2 square over L plus with M3 U3 square over L, and goes on will be M for Mn UNO square over L. So since the mass are same, the mass of the molecule are same, so I will get, M over L equals to U1 square plus U2 square plus U3 square Un square. Okay, alright, so now let's look at this. Go back to this. Okay, let me take another color pen. Alright, let's look at this. Now for this molecule, mean speed will be what? Mean speed will be U1 plus U2 plus U3 plus Un is equals to the divided by the total number of molecule. Okay, and then mean square speed, that means speed square first. Okay, so you get U1 square plus U2 square plus U3 square Un square over total number of molecule. So mean speed, the symbol will be mean speed. Mean square speed, the symbol will be like this. Okay, so that means this is equals to n times with mean square speed. So the formula becomes, for here the formula, okay, I don't have enough place already here. Okay, so here the formula will become m over L and mean square speed. Okay, from here it becomes like this, correct? Okay, so I'm just going to, so this will be the total impulsive force for n molecule in one direction. Okay, pressure of a gas is force over area. Okay, force over area. So force will be Nm over L mean square speed divided by area, which will be L times L, which will be L square. So you will get your formula as Nm mean square speed over L cube. So this is the pressure of a gas for n molecule in one direction. Okay, next we want to find the third stage for n molecule in three direction. Okay, x, y and z. Alright, we have a molecule here which is moving in x direction, which is correct, with the mean square speed for n molecule in x direction. N molecule in y direction will be mean square speed will be like this. N molecule in z direction will also be like this. Okay, we'll move with the mean square speed. So total mean square speed in three direction will be total mean square speed in three direction, symbol will be c square, will be what? In x direction plus y direction plus z direction. So it will be like this. Correct? So the pressure of a gas for one molecule in one direction is Nm. Okay, all right. So pressure of a gas for n molecule in three direction will be Nm over L cube. This thing here, okay, this thing here, mean square speed is equals to correct, total mean square speed divided by 3. So I substitute, I will get 1 over 3 mean square speed. So I arrange it properly, I get Newton meter 1 over 3, okay, L cube. Alright, okay, so this will be the formula. Okay, I didn't write it properly. I will write down for you properly. Nm so this will be the formula. So if you look at your textbook, you will get the formula 1 over 3 Nm mean square speed. Okay, 1 over 3 Nm mean square speed. Okay, all right. Now from here, what do you get, class? Okay, right. So this is how you get the pressure of a gas. So you need to know how to derive this formula. All right, so I haven't finished yet. Okay, so the formula you get this now, the pressure of a gas is 1 over 3 Newton meter over L cube mean square speed. Now from this formula, okay, if L cube is actually equals to the volume of the gas. Alright, that's why in theory kinetic of gases number 4, it says the volume of the gas molecule is negligible compared with the volume of the gas. Okay, so we are only interested with the volume of the gas. So here will be, the formula will be the pressure of a gas equals to 1/3 Newton meter per volume mean square speed. Okay, alright. If small n is equals to the number of molecule per unit volume, then the formula will change to pressure of a gas equals to 1/3 Nm mean square speed. Okay, so we have 1, we have 2, and we have 3. Okay, 3 will be if density is Nm over V, then the formula will be 1/3 rho mean square speed. So the pressure of a gas can be interpreted in 3 formulas. Okay, in 3 formulas. So please take note of this, of this, of this. Don't get confused with the small n. Yeah, the small n is very important because it is the number of molecule per unit volume. Alright, okay. Now class, what did I teach you today? I teach you today, in order to get the pressure of a gas, you have to divide into 1, 2 and 3 session. It is for 1 molecule in one direction, n molecule in one direction, and n molecule in 3 direction. And if you see me proving all this, you will notice that I have proved this according to the assumption of the theory kinetic of gas. Okay, alright.